So, welcome students, let us look at one more lecture on electronic systems for brain stimulation in the series of lectures on advanced neural science for engineers. So, initially if you look at it, we have seen fabrication. So, we have seen how to do fabrication of this neural implant, then we have seen the different characteristics that it has to satisfy to be a fairly good neural implant, if it is recording, if it is for stimulation and all those things. Then once everything is ready, now you connect it to the electrode interface board EIB, then there is a FPC cable. Now from there you will give the connection to electronic systems. Okay. Now this is a wireless pulse generator. So let us in this lecture I think we will not discuss much details about it, but I just want to give you emphasis of how does it look like. First of all, what is that you want to stimulate this brain region, right. Now these electrodes connected via this FPC connector, and that goes to this and that goes to the electronic system. So you have direct access to the brain and you have ground also, which generally we put it in the cerebellum area, right. This is the cerebellum area, and that ground also will be available for the electronic system. Between this you apply the potential and you know there is a current flow, are getting it. This is a global stimulation. What generally people do is they will take 2 electrodes that are present. Now we have 5 electrodes, right, 1, 2, 3, 4, 5. Out of them one they will make it as active, another one as a ground, and then they stimulate only this particular area. Anything is fine, does not matter, the concept remains same, right. For engineers the concept remains same, the application could be different, right. Now we already discussed in the previous lecture about why biphasic, right, because you should not damage the tissue. When you will damage the tissue, if you deposit excess charge, right. So this is how the biphasic pulse look like. The current and time, right. If you look at the current and time, the area under this graph will give me the charge, the area under this graph will give me the charge. After the end of the application of the pulse, you have the charge to be 0, the total charge that you supply to be 0. And also I just showed you some images here, right. If you look at it, this is how surgery will takes place. I am excited to show you. So we have seen neural implant and we have seen the fabrication of the neural implant. Then we will see the electronic systems. I will also show you how we will do surgery by using the equipment that is available. I am going to give you a demo on stereotaxic operators. How does it look like, for your information, right. So generally you see this rodent skin is removed, and then there is a skull bone that have to be drilled, and then we need to fix the screws for dental acrylic to sit in. Why dental acrylic is required, because you need to have the implant in place there, sturdy, alright, and then placement and all those things. These are just typically how does it look like, right. Now if you look at it, this is a typical the wireless architecture that I am proposing, but there are many other ways also to do. Now there is a microcontroller here. You see this is from PSOC, Cypress Semiconductors, and this microcontroller can be wirelessly controlled. The PSOC microcontroller as such does not have a microcontroller, but when it is integrated with BLE modules like HM10, right, all those things by which you can communicate with the PSOC 5 microcontroller by using the LabVIEW, right. Then this PSOC microcontroller has something called as IDAC pins, current digital to analog converter. These are IDAC, current digital to analog converter. These will act as a source, current sources or current sinks. right. So, why am I talking about current source and current swings? So, here if you see, look at it, there is a electrode tissue interface here, right. Now, you want to have something which is for generation as well as recording. Even though the slide says pulse generator, the emphasis is more on generation, because we are not going to discuss about the acquisition part, because we that is not the objective of this course. So, we do not talk about biosensing board, because this is commercially available and then it is supplied with the battery. Now, for this you can choose a switch, right. If you connect the switch, SPST switch, single pole single throw switch, if you connect it, then the current mirror block outputs will be in contact with the electrode tissue interface, otherwise they are in contact with this. By default it is in recording mode, the architecture right now. If you switch it, then that particular output blocks of current mirror will be passed to the electrode tissue interface, and these currents may not destroy this open BCI system. So, less worried about it. Now, what is this concept of current mirroring here? Why we are doing this? Now, if you look at this, there are 4 IDACs that are present in this microcontroller, and I have 5 electrodes, right. 5 electrodes on the right, 5 electrodes on the left. Let us say I want to stimulate all the electrodes at a time. Can I be able to do it? I cannot be able to do it, right. So, that is where the concept of current mirroring coming into picture, and this charge pump and all is required for voltage complaints with current mirror blocks, and then increase the range of current mirroring. So, here the basic block that is very much important to us is current mirror. Why current mirror and all, right? Because we want to stimulate many electrodes at a time. If I want to stimulate many electrodes at a time, we need to have a current mirror, right. So, let us look at it, how does it look like. So, how does the current mirror works is the basic current mirror I am discussing. So, you have this resistor for example, and there is a transistor. Now, when let us say this is NMOS transistor, there is a drain, there is a source and there is a gate, correct. Now, we connect these two, drain and gate, and we apply sufficient voltage, let us say plus 10 volt something, and source is connected to ground. This will be pushed towards saturation. Of course, this transistor will be in saturation, there is a current that flows, right. If you choose very minimal resistance, let us say 1 kilo ohm or something, correct. Now, because of that, this transistor is in saturation with some VGS. Similarly, if I have a current source coming out like this and you connect it to the transistor something like this, which is configured to be in right in saturation, let us say some voltage, okay, something. Now, this current, let us say this is around 1 milliampere current, right, current source, when it is connected in series with this transistor which is connected to be in saturation, it develops some voltage VGS, whatever is the voltage, let us 2 volts or something, let us now call it as VGS, right, and the current that is flowing through is nothing but right IDS, right, let us say assume IDS. Now, this IDS is going to be 1 milliampere. Now, how IDS and VGS are connected? IDS is mu n C ox W by L VGS minus VTH whole square by 2 into 1 plus lambda VDS. Now, for simplifying our discussions, let us make VDS this lambda to be 0, there are no saturation effects. So, I am not saying VDS to be 0, I am saying lambda equal to 0, right, let us assume that. for a simple discussion, because here you need to understand the cycle of electrophysiology labs, right. So, now what will happen is, now this current, okay, let me erase this part, the right part. Right. Now, the PSOC that we have, PSOC 5 LP microcontroller, has a IDAC pin, and this I can program it as a source or a sink. Let us say this is acting as a sink source with 1 milliampere output current. Now, this I will connect it to NMOS transistor, same thing, right, same story, you can visualize, right. And when you talk about source, now there is a provision in the PSOC 5 microcontroller that I can make it as a source or a sink or stop it completely, right. So, if I take I versus T for example, I can make it as a source, I can make it as a sink, I can stop it also, I can stop it, I can make it as a source, I can make it as a sink, whatever it is, I can play around with that. And this on time, T on time of this anodal pulse, T on time of the cathodal pulse, and T off time, anything can be programmed, and in real time, right. So, now what happens is, instead of directly supplying this to the brain, I am trying to supply through something, so that I can have multiple sources at a time, right. So, next what happens is this. Now, since I have this VGS, right, your IDS, instead of supplying directly to the brain, now what we do is we copy this IDS in the form of VGS, because 1 milliampere can have some voltage, let us say 3 volt or something, depending on V and C. Now, that I can copy across this this one more transistor, right. This, let us say this VGS 1 for M1, then I can have VGS 2 for M2, right. If I can make sure this transistor is in saturation, then the current that flows here is 1 milliampere, right. If this is 1 milliampere, obviously this also will be 1 milliampere, right. So, plus 10 volt, and this is where the load comes here, are you getting it, right. So, 1 milliampere if you pump, you will get 1 milliampere. Of course, there are some non-linearities will be there, that also can be addressed using different current mirror configurations, or slight non-linearity will be accepted as soon as you maintain, as long as you maintain this charge neutrality, right. Now, I have talked about only sourcing, right, there can be sink also, are getting, as soon as you maintain the charge neutrality. Now, what is this? This is current delivered to the load, right. You have one more network that delivers the current, which in terms of sink, are you getting it. So, there is M1, M2 like this, not only M1, M2, I can have M3, I can have M4, like this I can have multiple outputs at the same time, because this VGS is going to be same. VGS 1 is equal to VGS 2, this is VGS 3, VGS 4. According to the network configuration, VGS 1 is equal to VGS 2, that is equal to VGS 3, that is equal to VGS 4. If we can maintain M2, M3, M4, if you can bias this into saturation, then IDS 1 is equal to IDS 2 is equal to IDS 3 is equal to IDS 4. You understood that, right. So, this is how we can just do the current mirroring on an overview, correct. Now, you have one the issue with this is actually you have one network that is generating the source, this is one, let us say network 1 generates a source, network 2 generates a sink, some other network, let us say that is made of PMOS and all those things, right, and again the output is connected to the load. Okay, little tricky, I am not getting into details of that. So, the point here is network 1 and network 2 may not have exact matching transistors to maintain the charge equal to 0. So, what people can do generally is you have current mirror, right, you have current mirror configuration, you take only network 1 and you connect the output in the H bridge manner, right. So, when I say H bridge, how does it look like is this. Because two networks are generating, no? one network is generating cathodal, one network is generating anodal pulse. That is where the problem is coming, because charge neutrality will never be maintained as 0. The important thing is the charge neutrality, right. So, what you do right now is different tricky, right, little tricky. You have P sock, then you have source. Now, what you do is let us say I say sink, right, you have NMOS transistors, PMOS transistors that are coming into picture. Sorry, let me redraw this. Okay, let me erase all the ink, right. Our idea is to maintain the charge neutrality, no. So, let us say you have P sock and you have a sink pin, sink means the current flows inside, right. Now, you have PMOS that is connected, because this is a drain, this is a gate and source is connected to plus 5 volt or something, right. Now, output is coming, now this is a load, right, right. Now, let us say there is a switch here, switch 1 and there is a switch 2 and this is connected to ground. Now, let us say switch 1 is 1, switch 2 is 0, means the switches are connected like this. So, how the current flows? Current flows like assuming that transistors and everything is in, right. So, this is the direction. Now, you reverse it, let us say switch 1 is 1, switch 2 is 0, I mean switch 1 is 1, switch 2 is 1. Let us say for example, that means that you have a switch here which connects like this and there is a load and now the switch will connect back to this, because switch positions has been changed like this, right, and these are analog switches, okay. You can just program them and then accordingly it will switch. They are also called SPDT switches, single pole double throw switch. So, now what is the current direction, right? If you look at the current direction, now you are not changing this network, right, it is the same network, this is the same network, right, this is the same network 1. So, now the current will flow in this direction, positive, negative. Earlier, if I take this as a load, this is positive, negative, it is going like this. Now, in the second phase, it is going like this, correct. So, there is a very high chances, or at least electrical point of view, there are other issues also involved in this, but at least at the electrical point of view, the charge that is delivered between the, I mean during the cathodal and anodal pulse, okay, generation, this is cathodal, let us say this is anodal, it is okay, whatever it is, okay. Since the same network is generating both cathodal as well as anodal, there is a very high chance that the charge neutrality will be maintained. That is very much important. Okay. So, I am stopping it here. In the next session, as I told you, in the next it's not a next session. Okay. So, the next is going to be a video where I will show you how the surgery is performed on the rat. I will show you the rat stereotaxic operators and microscope and the various other tools that are required for the surgery, and how the little bit of Faraday cage looks like, and then how the environment there looks like. Okay. So, let me show you the video now.